Hello everyone. Today I want to give you an overview and a brief explanation of the design of Agon light that you see now. Not only to help you understand Agon light and maybe design your own variant, because this is an open source design, but also in the hope that maybe you can gather some tips and tricks and some best practices that may help you in your own designs. So not only your schematics, your logic designs, but also your PCB designs, the physical layout of the boards you make. So let's get right into it. This is the schematic diagram of Agon. It's one page of 5. There are 4 other pages. I'm looking at the CPU page now. There's also the memory page, the audio video page, power supply unit and IOs, and the GPIOs page. So let's start from the CPU. I'm only going to tell you what does what. Perhaps I'll say something about the why, but I'm not going to tell you the hows, because the hows would require a lecture in electronics, which would be redundant because these lectures are most likely available online. So I'll just tell you the whats and some of the whys, so you have reference points and you know the keywords to look further, to educate yourself further if you're interested. Okay, so this is the main chip in Agon. This is the CPU. In reality, it's more than a CPU. This is a little system on a chip. It's a microcontroller unit. Has more than just the CPU core. This is the key chip. The first thing you notice that there are lots of little bypass capacitors everywhere around the main chip. Here you have them as well. Here on the other side, over there, there, and there, and so here below. They are everywhere. So why so many bypass capacitors? Well, modern wisdom is that only one would do, perhaps the 10 microfarad capacitor, because these SMD capacitors are so small, they hardly have any leads. And without leads, they don't have any inductive reactance. So you don't need to use multiple, you just need to calculate the right value given the resonant frequencies of the power distribution network. Well, the problem is it's a pain in the neck to calculate that or to use expensive tools to simulate and give you that value. So I didn't want to do it. I just preferred to cover an entire range of frequencies by putting several, or 3 in this case, values on every VDD or VCC input of the chip as bypass. So I was just being lazy. The only bad thing that this gives you is not the price. This thing costs fractions of cents, but it makes the layout job a little more difficult because you have to put all 3 capacitors close to the respective VDD pin. Otherwise, they don't do their job. And the more capacitors you have to put close, physically close to a pin, the more complicated your layout gets. You also notice that there are some 33 ohm resistors in certain places. Here, there, and there, here. And you will notice that I'm adding them on the clock output of the CPU and on some key control signals like read, write, chip select. This is the SPI clock output, and this is the master output signal, slave input of the SPI signal. These 2 signals here, this and this, they go to the micro SD card port. Now, why am I using these little resistors, inline resistors? It is just for impedance matching to reduce the amplitude of ringing. To absorb some of the high frequency signal reflections, because the traces on the board, we have an impedance of about 50 ohm. The output impedance of a normal CMOS pin is between 10 and 15 ohm. So if you add 33 ohm to that, you have impedance matching. And in practice, what that will mean is that the higher frequency components of these signals that will get reflected because of an impedance mismatch later on, they will get absorbed by these little resistors. These resistors, together with the normal parasitic capacitance on the board, will work as a low-pass filter and will absorb the higher frequencies and therefore reduce the amplitude of ringing. And for the control signals, this is important because you don't want the memory to get a false write signal and then capture whatever trash is on the bus before it actually should capture the contents of the bus. So, and ringing could induce this kind of thing, and these are active low signals. If you have a ringing on the signal that goes quite low, below, and this is the maximum of 3.3 volts. If it goes below 2, yeah, you have a problem. The memory may perform a write when it's not supposed to and contaminate its contents. And so that's why I use these resistors on the key control lines. They would also help on the data lines and address lines. But yeah, that goes too far. It would be too many resistors, and I didn't want to complicate my life that much. Moreover, in Agon, the data lines and the address lines, they are point-to-point lines. They have basically no fan-out, a fan-out of 1. They only go from the CPU to the memory, nowhere else. So you shouldn't have too much of a impedance mismatch or reflection problem there. So I didn't add those resistors in that case. Now, these two chips here, this and this, these are just buffers. And there are two reasons I am using them. One is that they have this output enable. So by inactivating the output enable, I can just shut off these two buffers and isolate these two lines that come from the CPU and go to the audio-video coprocessor, the ESP32. I can isolate them by creating a high impedance barrier here. And then it is as if those two lines are not connected. And that is handy because the ESP32 is very sensitive when it's in programming mode. And sometimes it doesn't allow itself to be programmed unless these two lines that go to it are in a high impedance state. So this allows me to put the two lines in a high impedance state by just placing a shunt here on this header. If I put a shunt on this header, this point here, which is normally at 3.3 volts, will go to ground. And this is an inverter. This chip here is an inverter. So this will go high. And since the output enable is active low, it will disable these two buffers and isolate the ESP32 from the CPU. The other reason is that these are basically buffers, so they strengthen the signal midway through their path. So it reduces amplitude loss of the signal because it's like repeaters, it's like Wi-Fi repeaters if you wish. Now I'm using the 33 ohm resistors on these lines as well. You see them here, there again, and the purpose is the same. It's to absorb the high frequency reflections that cause ringing and reduce the amplitude of the ringing. The reset line has a little filter capacitor of 100 nanofarad, and that is just to prevent that interference on this line bring the CPU into a reset state when it's not supposed to. This filter capacitor here will filter out whatever interference or lack of stability is on that line and prevent the CPU going into reset when it shouldn't. Now, these resistors here that you see here, they are just pull-ups. And the idea is you pull these control signals from the CPU high so that for these signals to be active, the CPU actively has to pull them low. And the CPU can do that because they're connected to 3.3 volts through a fairly large resistor, fairly large resistance resistor. So the CPU can counter that, can sink enough current to counter the 3.3 volts through these large resistors here of 10k ohm. But this ensures that you never get a false read or a false write or a false chip select. And it defines these control signals at all times, even when the CPU perhaps is not driving them, although the CPU will be always driving them. So that's basically it. A lot of what you see here is probably unnecessary. One could probably get away without these buffers because Agon is designed cleanly enough that the ESP32 will be in a programming state, even if these lines here are not in high impedance. Probably could get away without the 33 ohm resistors. Probably could get away with only one bypass capacitor, maybe 100 nanofarad would do, instead of 3 values for all the VDD signals. But yeah, it's a question of how robust you want to make your design. All these components that may be unnecessary, they are dirt cheap, fractions of cents. The only bad thing you get from them is that your layout becomes a little bit more complex. But I decided to bite that bullet and make a more robust board that isn't more expensive, and in any way significantly more expensive because of this extra robustness. All right, let's go to the next page. That's a very simple page. This is just the SRAM, the system SRAM, with two values of bypass capacitors on both VCC inputs. These are just the address lines, the chip select, the write, and the read signal from the CPU. They are connected point to point, fan out of one. This is the main oscillator. Instead of building an oscillator with a crystal and separate capacitors, I just chose to use a fully integrated 4-pin oscillator. The 33 ohm resistor is there to remove high impedance ringing, to absorb the high frequency reflections. This resistor here, yeah, you probably don't need it. It's basically just a pull-up resistor. You probably can connect 3.3 volts straight into this pin 1, because this has a very high input impedance. But yeah, just to be extra safe, put a current limiting pull-up in there. And this is just another bypass capacitor to even out the power signal, to keep it clean going into the oscillator. Now this is the reset circuitry. It's a very simple open collector circuit. The way this works, let's ignore this part for now. Let's leave that out. Let's focus on this part here. This is just a startup reset timer. When a computer is turned on, this capacitor here is discharged. So current will flow slowly from 3.3 volts through this large resistor here. So small current will trickle through this large resistor and charge this capacitor. In the beginning, because the capacitor is discharged, this point will be low at ground level. And therefore, the reset will be active, because reset is active low. So when you turn the computer on, this line will be low or active. The computer will be in a reset state. But with this trickle of current here slowly charging the capacitor, after a few fractions of a second, this will be high, and the reset signal will go high and therefore inactive. And then the computer can go into normal operation. This is the reset button. And what happens when you press the reset button is that you connect this point 2 to point 1. Point 1 is ground. So when you connect 2 to ground, you will discharge this capacitor through this line here. This capacitor will be discharged to ground. And this will be at ground again, and therefore the computer will go back to a reset state. Now, what does reset the computer? Well, when you turn it on, it is reset. When you press the reset button, it is reset. But there is also another circuit here. This is just a VCC supervisor. It's a very simple circuit. It keeps on listening to the 3.3 volt line. And it has a little bypass capacitor. Not bypass, this is more a filter capacitor, just to make sure that the supervisor doesn't pick up on noise, but picks up on the actual value of the 3.3 volt power rail. It keeps on listening to it, and if that power rail goes too low, it will pull the reset line in pin 2 down and cause a reset. And the idea is to reset the computer if the power rail goes too low, because then the operation becomes unreliable and unpredictable. So this is just a VCC supervisor. Now let's go to the audio-video circuit. I will really not go into the details of this one, otherwise it will take forever. All these capacitors are bypass capacitors. Same reason you saw in the other slide. I am using now 2 values, not 3. There is a little inductor here, little bead, little coil, that has the same purpose. Capacitors resist changing voltage. They compensate for noise and variations in the voltage. The inductor does the same thing, but for current. It resists changes in current. So you could consider adding this coil here as another form of bypass, in the sense that it tries to keep the power level stable into these 2 inputs of the ESP32. The VDDA 3P3 are 2 inputs, and you want them to have a very, very stable power signal. Let's see, these are the 2 lines that come from the CPU, the serial lines. This is a transmitter coming from the CPU, goes into IO34, which is the receiver of the ESP32. And this is the receiver of the EZ80, which connects via 33 ohm resistor to reduce the amplitude of the ringing into IO2 of the ESP32, and IO2 is the transmitter of the ESP32. So the ESP32 transmits that way and receives this way. This is the sound circuitry. The sound is produced by the ESP32. It comes from this pin 14, which is IO25 of the ESP32, connects here. And then you basically just have a little filter to make the sound more pleasant to hear. So this is just an RC filter to condition the audio signal. This is a safety diode. It just makes sure, because this line here is connected to an output port. So if people stick their finger in there or connect a plug in there that is statically charged through this double-sided diode, it's actually two diodes, that excess voltage is drained to ground before it goes into the rest of the circuit and gets into the ESP32 through this pin. So this is just an overvoltage protection diode, or voltage transient suppression, and whatever you want to call it. After this diode, the same audio signal goes into these two connectors of the audio jack. So this is a stereo audio jack, but I'm using it for two identical mono signals. So it's not stereo sound. You don't get two different signals. It's the same signal going to both connectors. So you can drive two speakers with the same mono signal. Now, the way this is constructed is that if there is no plug inserted into this connector, then this line is connected to this line here, which goes there. The same for this line. If there is no plug inserted, then this line here will go this way to buzz, which is again the buzzer signal. So the buzzer will buzz if there is no connector inserted in the audio jack, but if a connector is inserted, then this connection here is broken, because this little connection points here, they will be stretched down in this case, and this one will be stretched up, and this connection point will go open, and there will be no signal to the buzzer. So when you connect speakers to Agon light, the buzzer goes silent. And if you disconnect the speaker, the buzzer will produce the sounds, except if you remove this shunt on this header, and then you silence the buzzer under all circumstances. Now this resistor and transistor here, it's just an extremely simple amplifier that sort of levels the audio signal to the middle of the 0 to 3.3 volt scale. So it oscillates around 1.65 volts. It oscillates around that value, so we capture the full range of motion of the membrane in the piezo buzzer. So it's an amplifier and a way to sort of center the audio signal in the middle of the oscillation range. That's all there is to it. Now this is the USB bridge. It would translate the USB signals that come from the USB port into serial signals, these two, that go to the ESP32. That's basically what it does. These are bypass capacitors. Now, the rest of what you see, you have to read the data sheet to really understand what these two capacitors and what this resistor are doing. These are the two lines that come from the USB jacket, the USB port. They form a differential pair, D plus and D minus. They come in here, and then after the translation done by this chip, they become serial signals that go into the ESP32. Let me see here. Yeah, these two signals here, here are these two signals here. This diode here is the most common diode in the world. I'm just using it for the voltage drop. That's all I'm using it for, to reduce the 5 volts to a little over 4 volts for the V-bus voltage of the bridge. Now, to understand why these values, have a look at the data sheet. Now, this is just an extremely simple DAC, a digital to analog converter, that feeds the VGA signals. This is the VGA port. All these lines here come from the ESP32. So if you look for IO22, let's see where that's here, IO22. If you look for IO21, it's there. If you look for IO19, it's there. So these are just 6 digital signals that come from the ESP32. And through these 6 resistors, they are translated into analog values between 0 and 0.7 volts. The first pair is for red. The second pair is for green. The final pair is for blue. So it basically forms the R, G, B signals that go to the VGA connector. And the value of these resistors is calculated in such a way that for maximum brightness of that color, you get 0.7 volts, although you're starting from 3.3. And from minimum level of that color, not brightness level, for minimum level of that color, you should get a very, very low value, very close to 0 volts. It so happens that I found resistors with almost the exact value that comes out of the calculations. They are not common, but there was a lot of stock available for these strange values. So I decided to use the strange values and not sacrifice color accuracy just to use more common values, because yeah, this stuff is made. At least in China at LCSC, there was a lot of stock of these resistors. These are again just safety diodes. They keep on listening to the lines they are connected to, and if there is overvoltage, then they open up and the extra energy flows to ground and spares the rest of the circuit. I'll leave this for last. This is just the terminal memory, the memory that's available only to the ESP32. So you have chip select and then the serial lines, including a clock line. All of these PSRAM something lines, they come from here, from the ESP32. So they are basically, I'm not drawing the lines because it would be too complicated, but all these lines here come from the ESP32. This is a serial memory, 8 megabytes. Because it's serial, it gets a clock, serial clock from the ESP32. It comes from there. It's a very high-speed memory, can operate at 133 megahertz. This is just a pull-up resistor for the chip enable, so the RAM doesn't become enabled when it's not supposed to, and this is just a bypass capacitor. Now this is an extremely simple two-transistor circuit to decide when to reset the ESP32 based on the serial control signals, RTS and DTR. And it will set these 2 bits here to the appropriate mode. So the ESP32 has different modes, and given the control signals that you get, the modes should be set accordingly. I'm not going to go into the details. The only thing I'll speak a little bit more about is this header and this resistor. This is a pull-down resistor for the IO0 line, and the reason for that is that the ESP32, again, is known to be a sensitive device, and sometimes it doesn't go into programming mode, even if IO0 is being driven low. So to strengthen that, we add this pull-down resistor. But I put a header to give the user the option to take this resistor, this pull-down, out of the circuit by removing the shunt on this header, because the opposite might happen as well. It may go into programming mode when it's not supposed to. I haven't seen these problems in the final Agon prototype. I did see it in the first prototype, not in the Agon Lite of revision 1 that has been released already. But I thought, why not make sure that whatever happens, there will not really be a problem, because the user can always put the shunt to program the ESP32 and then remove it when you want Agon to just run an application and not be in programming mode. So that's basically it. These key signals here, they are basically serial control signals. They are the same signals repeated twice, and they come from here, from the USB to serial bridge, which is U4. And depending on whether these signals are high or low, you need to reset the ESP32 or put the ESP32 in programming mode. This does the programming mode, and this is the reset for the ESP32. It also happens to be a global system reset. So after the ESP32 is programmed and it's meant to be reset, the entire system will be reset, not only the ESP32. Now that's the power supply unit here below. Extremely simple. Well, not including these two guys. These two guys are separate. It's a very simple power supply. It gets 5 volts from the USB connector, that's VCC here. Then the two data lines, the differential pair of USB are D minus and D plus. They are the ones that go to the USB bridge. They also have the safety diodes here to prevent overvoltage. There is a very, very simple RC filter here with 1 picofarad capacitors and 2 10 ohm resistors, just to filter out some of the noise. And this pair is routed very close together, which acts as an extra sort of common mode filter. And then they go into the USB bridge, which we just saw in the previous slide. They are these two lines here, D minus and D plus. So this is not the power supply. This is just the data signals coming from USB. Now the lower part here, that's all the power supply. This stuff is the power supply, which is based on VCC and ground. Now, normally you would just connect the ground signal, which is this signal 4 here, straight to ground of the board. And you would also ground the can of the connector, the metal jacket of the connector, also to ground. This is what I think most people would do. The reason I added a large resistor and a little inductor is the following. Both the resistor and the inductor will resist large current flow. The inductor does it because that's what inductors do, and the resistor does it because it keeps the current very low when it's flowing to ground. And the reason is the following. Remember, there will be a cable connected here, a USB cable. And a cable, even if it's insulated, there are variations. There is interference involved. And what could happen is that the ground level of the transmitter, your PC that you connect to the USB port, that ground level through the cable may fluctuate. And if it fluctuates, then the reference for the D plus and D minus signal will change. So what you want to do, you want that the can and the ground of the Agon light board are not immediately anchored to the ground reference of the Agon light board. Otherwise, there will be different references. There will be a slightly floating ground reference on the transmitter side, and Agon will have a different reference, and that could lead to a misinterpretation of the signal levels. So what these two things do is, if the ground fluctuates on the cable or on the transmitter, this will give more time for the socket, the connector here, to fluctuate with the cable, and therefore follow the signal reference of the cable and the transmitter, instead of anchoring everything to the local ground reference of the Agon board. That's the idea, is to give the signal time to maintain the same reference, even if that reference fluctuates, before it's cemented to the reference of the Agon light board. Now, is this really necessary? Most likely not. But again, it's the kind of thing that costs nothing, doesn't make the layout much more complicated, so why not? Now, this is just a clamp. It works as a safety if there is overvoltage, then this diode here will open, even though it's biased the other way around. It will open and the excess energy will flow to ground. This is just a fuse. It's a solid state fuse, so when it opens, you don't need to replace it, because once the excess voltage, or the excess current in this case, gets reduced and current goes back to normal, then it reconstitutes itself. So it's not something that you ever need to replace, but it works as a fuse in the case of excess current. This works in the case of excess voltage. And this is just a little coil, a little bead, to stabilize the current. Now, again, 10 nanofarad, that's just decoupling, and through a resistor you light up the LED, the power LED, to indicate that Agon light is on. Then there is more significant decoupling here, another safety diode, a bi-directional voltage transient suppression diode connected to the 5-volt line. Could somebody put their finger somewhere in the 5-volt line and induce static discharge? Hopefully this diode will prevent catastrophe. This is a low dropout regulator that will convert the 5-volt input into 3.3 volts. And it needs to be low dropout because you don't have much room for maneuver. From 5 to 3.3 is only 1.7 volt. And usually you don't get the 5. You get 4.6 here when you connect to USB because there are losses on the cable, losses elsewhere. So you really need a low dropout that will maintain 3.3 volts even when the input voltage is very low. Now this is more decoupling. This is a large 407 microfarad, very low ESR electrolytic capacitor. There are two of them. They are both very low ESR. And then more normal decoupling like a 10 microfarad tantalum and the usual ceramic 100 nanofarad. And then you get the 3.3 volt power rail. This is the Zdi connector used to program the firmware of the EZ80. It's a subset of JTAG. It has only 3 signals, a reset, the clock, and the data line. That's all there is to it. You need to pull them both high. That's just the convention of the Zdi. I think these are open collector signals, I think, but you need to pull them high just for safety. Maybe they are not open collector, but you do need to pull them high. There is a safety diode here because, again, this is people will insert something in here. You never know whether there will be a static discharge. So this is just to protect the power rail from whatever discharges may happen. So these are the input signals that come from Zdi. They are all also protected with this TVS diodes. This is the micro SD card connection circuitry. You have pull-ups, and you should have pull-ups. These are bypass capacitors to make sure the power level is correct because you need to feed power here, VDD. You need to feed power to the micro SD card. So this ensures that the power levels the card sees. The micro SD card is not just memory. There's a circuit in it that needs to be powered on. So you need to stabilize, or you want to stabilize the power seen by the card. Again, just protection diodes down here. And this 33 ohm on the master in slave out. This is the slave, so this is the output line of the slave. So you put a 33 ohm resistor there to absorb the ringing, the higher frequency reflections. The chip detect signal is not being used. Don't really need to use that. And the CAN in this case is fully connected to ground because unlike here, where you have potentially a long cable, here the card is just inserted locally, so you can just anchor everything immediately to ground. You don't need to follow a fluctuating ground level of a cable or a transmitter and just anchor everything immediately. Now this is the keyboard readout circuit. The only reason there are a few components here is that the PS2 keyboard, the signals are referenced to 5 volts. These are TTL level signals. And the ESP32 needs to see signals referenced to 3.3 volts, not 5 volts. So you need to bridge the 3.3 voltage domain here to the 5 volt voltage domain there. And that's what this circuit does. It bridges the two using little MOSFETs with an embedded diode. This is a bi-directional signal, so you want a little embedded diode to make sure that happens. This is just a pull up to 5 here and here. This is a pull up to 3.3 volts here and here. And this is just the base bias. Now these are textbook circuits for bridging two voltage domains, literally textbook. Even the values, you will find them, that's what almost everyone uses. So I take no credit for this. This is just textbook stuff. And I pull up two of the GPIOs of the ESP32. Maybe this part of the circuit should have been here, close to the ESP32. But I decided to put them here because these are IOs. And this is the power supply and IO diagram. They are being pulled up just because I wanted to make Agon Light compatible with FabGL, to support FabGL. And these are the mouse lines that FabGL assumes to be present, even though in Agon they are not used. But FabGL expects the mouse lines to be pulled up. If you don't pull them up, then FabGL doesn't work. So that's why I put these two pull-ups there to ensure compatibility of this hardware with FabGL. And finally, the last diagram, it's the GPIO, which is basically a connector, all the available GPIOs plus SCL and SDA, and plus the SPI lines, MOSI, SPI clock, MISO, and clock out. And then 20 GPIOs that they are all available on the control port of Agon, which I call GPIO here. This is just, again, voltage suppression, excess voltage or transient voltage suppression diode. It's bidirectional. So if there is a static discharge here over voltage, the energy will be drained to ground. This is the decoupling capacitor, because this 3.3 volt line is supposed to allow users to power an external circuit from the Agon control port. So I wanted to put a little decoupling here to make sure that the external circuit sees a stable power rail. Same thing for these two. These are also decoupling capacitors, this one and this one. But now it's for the 5 volt line, because the 5 volt pin 31 here on this connector, the control connector, can also be used to power an external circuit. And therefore, these two decoupling capacitors to ensure a stable power level. Now, the 5 volt pin 31, can also be used to power Agon instead of the USB port. In case you want to plug Agon into a backplane already pre-programmed, so you don't need to use the USB line. If that backplane has 5 volts, you can power Agon this way. And that's why I have the little bead here to make sure that the current is stable. There is another fuse, and there is another clamp, just protection for the rest of Agon. This is the access bus header. I put it in there to make it easy for people designing custom cases to add a small, for instance, status display that could be internally connected to this header and drive whatever message people want to display on that second small display that's not connected to the VGA line. So we need these two signals, SDA and SCL. These are the I2C signals. They need to be pulled up because these two are indeed open collector signals. So they will not define a high level. You have to pull them up if the circuit is to work. The header also needs 5 volt. That's the convention for access bus. So I added another decoupling capacitor there, 10 microfarad, to stabilize the 5 volt line towards the display, whatever you connect to this, and transient voltage, bidirectional transient voltage suppression diodes. And that's it. That's it for the schematics, other than transient voltage suppressions for all the GPIOs and all the logic signals. Because, you know, I am a hobbyist too. I know that we insert little cables on these pins of the control port without paying much attention, and you know, there is always a risk of static discharge, and I don't want people to lose an entire Agon just because of a static discharge in one of these ports. So this voltage, transient voltage suppression diodes will make sure that the static charge flows to ground and gets dissipated without ruining the circuit, unless of course you put a major overvoltage there, then even these diodes will not suffice. But for all the usual everyday accidents, this should be enough protection. It does increase the cost of Agon by a few euros or a few dollars, but I think it's worthwhile to pay those extra few euros and not have your Agon ruined just because of the normal accidents that happen on a workbench. So this is pretty much it. We are now going to look at the PCB design, the layout. Agon's board has 4 layers. You can see them here. It's the top layer, that's the bottom layer. Both have signals, both the top layer and the bottom layer have the logic signals. And then 2 inner planes. That's inner plane 1, which is ground, and inner plane 2, which is VCC. Very simple, just 4 layers, out of which only 2 are actual signal layers, and the signal layers are the ones that are visible from the outside because they are the top and the bottom layer. Now let's first get ourselves oriented on what is where. This is the USB port. This is just that filter for the USB signal that you've seen. That's the differential pair, D plus and D minus. Notice that they are routed as close together as the design rules would allow. And the reason is that because this is a differential pair, D minus and D plus, you want them to couple to one another. You want there to be common mode here because it will help filter out extra interference that has nothing to do with these two signals. So this is a difference with respect to any other lines. You don't want two lines that are unrelated to one another to be routed close, because if they couple to each other, that's a form of interference that we call crosstalk, and we don't want that. But in the case of a differential pair, that's precisely what you want. You want to couple them, to have common mode. It works like a very small inductive filter of interference. So we keep them routed together until they connect to the USB bridge in here. Now, on this side here, that's just the protection circuitry. So this is the power line. This is the 5-volt line that comes from USB. So there is a little clamp for excess voltage. There is a fuse for excess current. And then the rest you've seen. That's the power LED with a little resistor to drive it. And then there are a lot of decoupling capacitors, small decoupling capacitors here, plus a large one here. This is the one of the large electrolytic capacitors. And then the 5-volt line goes into the Ldo regulator, which produces the 3.3-volt line. And that's the ground reference. Now, the Ldo regulator has an open metal area here. It's connected to 3.3 volts. And the reason is the tab of the regulator, the metal on the back of the regulator, it is 3.3 volts. So when you solder the regulator here and you bend it down so it goes flush with this exposed metal, you will have a huge area for the regulator to pass down the 3.3 volts to the board. Instead of just a pin, you have this huge area, which will also work as a sort of heatsink. All these little vias here, they are large because they are not meant only to connect this metal area to the 3.3 volt power plane in one of the inner layers. They also work as thermal vias, basically to spread the heat and prevent heat accumulation. So that's the power supply part. There is more of it on this other side. This is if you want to power Agon from this pin instead of from the USB part. Then you have the same thing. You have the fuse, you have the clamp, you have two large decoupling capacitors, and those join to the 5-volt rail on this side. And if you look at it as a whole and you highlight the 5-volt rail, maybe I have to go to the bottom layer where it's actually routed. See, this is the 5-volt rail. So whether it's powered from the USB or powered from the control port, it goes towards the same rail where it's distributed not only to the regulator here, but it also goes to the PS2 keyboard port, which requires 5 volts, because that's the PS2 convention, and to the access bus port, where convention requires that it be there to power whatever access bus device you connect to that header. Now, the most important part of the layout is this area here between the bridge, the ESP32, and the CPU. That's the critical area. The bridge, because the USB signals to program the ESP32 are high-speed signals. And this, because that's the communication between the CPU and the video processor, which is should be protected, should be fairly high speed, so you don't want these lines to be long, and you don't want the lines between these two sides to be long. Now, from the USB bridge to the ESP32, which is here, you can't see from the bottom layer, but the signals go this way, and then they pass through this resistors here, and then they go down to the bottom layer across the two inner planes, and from there they will get, let me see if I can show you just by highlighting. From there, see that you will get here to the input of the ESP32, and in this one here to here, the input of the ESP32. Now notice that there are two ground vias right next to these two signal vias here, and here as well, a ground via right next to this one, and a ground via right next to this one. Now you will see this across the board. For all signals, I put a ground via as close to it as the design rules will allow me to do. And these vias, sometimes they are called return path vias or transfer vias. These are two slightly different things, but in this case they are playing both roles. I don't have time to explain in one video what exactly this is. There's a lot of theory involved, but the point is the following. Every time a signal goes from a driver to a receiver, like in this case it goes from this driver resistor here to the ESP32, every time the signal goes from here to there, current has to return from the receiver back to the ground. Every signal, every electrical signal is a closed loop. If you don't provide a return path ground via, so the signal the current can return through this via, the circuit will find a return path somewhere. And what will happen is that the return current will spread itself around a large part of the board, looking for the lowest impedance return path that is available. And it will always find something. But in the process of finding something, it will spread itself and interfere with the other signals and reduce your signal integrity. You get this common mode energy, and in this case you don't want the common mode energy because these signals now are not differential signals, they are independent ones. So to make sure that the return path is the one you decide and it doesn't spread and doesn't interfere with anything else, you put ground vias next to every signal via, if you can. Often that's not practical, but in this case I could do it. So Agon Light always has a return path ground via next, very close to every signal via. The other role this plays is, you could say it's more or less the same thing as a return path, but it's worded in a different way. When you call it a transfer via, what you're saying is the following. These signals here on the top of the board, they are referenced to the ground plane in inner layer 1, this layer, which is right underneath them. So this in red is the top layer, and what you're seeing now in this light greenish, that's the ground plane right underneath the top layer. So every signal going through these traces on the top layer are coupled to the ground plane underneath. And by coupled, what I mean is that when current flows through any trace, it produces electromagnetic field fringes. And what you want is that those fringes remain very small and very localized, because if they spread out, they will interfere with the other traces around. And then you get crosstalk, which you don't want. It's a form of interference. So to keep the field fringes very compact and not allowing them to spread, you put a ground plane or a VCC plane right underneath the signal traces, so they coupled vertically downwards to the plane underneath, as opposed to coupling sideways to the neighboring traces. So that's why you want a ground plane underneath as the reference plane. The problem is when a signal goes through a via like this, all the way to the back of the board, now you are 3 layers away. And the reference plane for the bottom layer, for this layer here in blue, the reference plane is inner 2. That's the one that's closest to it, or right above it. So what happens is that when the signal goes down from the top layer to the bottom layer, the reference plane changes. On the top, the reference plane is ground. For the bottom, here the signal is in blue, at the very back of the board, the reference plane will be VCC, because inner 2 is VCC. You see, this plane here is VCC. And when you have this change of reference plane, to keep the field compact, preventing it from spreading around, you need a via ground or VCC right next to the signal, so the plane fringes, when the signal fringes, the electromagnetic field fringes, when they go vertical and down the board, they couple vertically to the via next to it. Now I'm using always ground vias because these are also return path vias, not only reference vias. So long explanation, but hopefully it helps you understand why there are all these little vias here everywhere on this board, and some of them are actually ground, others are just close to signals. You see this one here, this one here, this one there, this one there, it's close to this one, that's close to this one is close to that. These are all return path and reference vias, because the signals have to cross two planes when they go to the back of the board or the other way around. That's basically it. Now, the other reason for some other vias is what we call stitching vias. Like these vias here, they are stitching vias. And their objective is the following. I copper flooded the top layer with VCC. In red here, all this copper around, this is VCC. And the idea is to create a sort of a built-in bypass capacitor distributed across the board, because you have a lot of metal on the top layer, a lot of red, and right underneath it is the metal plane that is ground. Inner one is ground, you see? So by putting a lot of copper at 3.3 volts on top, you create a sort of board-sized distributed capacitor, because you have 3.3 volts and right underneath you have a plane at ground. So this becomes a capacitor that helps with bypass, keeps the power plane even more stable. But of course, for this to work, you have to make sure that this copper flooded area here in red is connected to the VCC plane, which is inner 2. So you see these little connecting vias that you see here in inner 2 without a border area around them, they are there to connect inner 2 to the copper flooded area on the top layer and make sure that indeed there is 3.3 volts everywhere. And you might say, well, but only one is enough, or a few, right? Yes, if you're thinking in terms of low speed, but at high speed, you need a stitching via for about every 1/10 of the distance covered by the electromagnetic field of the highest harmonic during one period. So let's say the highest harmonic in the circuit is 1 gigahertz, which has a period of 1 nanosecond. So at the speed of light, the field covers 30 centimeters in 1 nanosecond. So we would need a stitching via at least every 3 centimeters, which is 1/10 of the 30 centimeters covered in the period of the highest frequency harmonic. Because otherwise, the voltage doesn't have time to get to where it's needed before there is already a switch and things already changed. And you may say, well, Agon light runs at only 18.432 megahertz. That's not high. It's only high speed at around 250 megahertz, right? So you don't need to worry. Well, that's not really true, because although the clock speed of Agon light is low, 18.432 megahertz, you have to keep in mind that the harmonic content of the signals has much higher frequencies. If the rise times and the fall times of the signals are very low, if you do a Fourier decomposition of the signal, frequency spectrum analysis, you will see that there are strong frequency components even at 10 times the clock speed. So in the case of Agon, 180.432. It may go up to almost 500 megahertz. They are less significant, but it may go that high. So, it costs nothing to add these stitching vias. So I stitched everything. These are VCC stitching vias, and these are ground stitching vias, because the same rationale applies on the other side. On the back of the board, the bottom layer is copper flooded with ground, so you need to connect this. These are the vias that you see there, and where else? Here. You need to connect them to the ground plane, which is inner 1. And then you might ask, well, why don't you just change the order? You make inner 1 VCC and inner to ground, and then they are all close together. Well, then you lose that effect of a capacitor, because I copper flooded everything at VCC here. It also helps give me this large area here to connect 3.3 volts coming out of the regulator to a lot of metal space here. So if you have VCC on top, the next underneath needs to be ground to form the capacitor. And then the next after that needs to be VCC again. And then the one after that needs to be ground again. You want to swap out ground and VCC to alternate them as you go down the layer stack. And that's why you have copper flood with VCC on the top layer. Then you have a ground inner plane, then a VCC inner plane, then you copper flood with ground on the bottom layer in blue. That's the idea. Now, I think I spoke about most of the relevant things, but I tried, when it comes to the floor planning, I tried to keep this line here. This is the transmitter, the UART transmitter of the CPU that talks or sends display list commands to the ESP32, which plays the role of graphics processor or video display processor. This is the critical line that needs to be protected and be at a very high speed. So you see it's a very short line here. It has a 33 ohm resistor here to reduce the ringing and the reflections. Then it goes into the buffer, and it comes out of the buffer here, another 33 ohm resistor to reduce the reflections, and then a very short line into the input of the ESP32. And so this is the line that needed to be the shortest. I also tried to insulate this line as much as possible. So you see here lots of 3.3 volt vias on the one side of this line and lots of ground vias on the other side of this line. This prevents crosstalk. It prevents any field fringes that are beyond the two sides from interfering with this line, that is the protected line. And on the other side, I couldn't go too far in the protection because the pins here are very close together. I need to use this pin for something else. But I put vias on them very close to the pin, so that these lines are very short as possible. And then I put a ground via here and a VCC via here to insulate this line. And indeed, this line here, it comes from there, goes to there, and then there and there. It has near perfect signal integrity. I made the measurements, and it's very, very good. So that's about it. I think that's all I wanted to say. The rest is just, trying to keep the lines short and as far apart as possible. Like here, because of the normal pin pitch of this package, these lines have to be close together on this area here. But as soon as I can space them out more, I do space them out. And then if I can space them out a bit more, then I do space them out more. And here, even more. So I try to space them out as much as I can to prevent crosstalk. Again, this idea, I see some hobbyists designing boards, and they like to keep the line very neatly close together because it looks good. Well, do you want to make a board that works well, or do you want to make a board that looks good? If you want a board that works well, you keep non-differential lines that are not part of a differential pair. You keep them as far apart as you can to prevent crosstalk. And you also want to minimize the number of bends on the line. Like this is a bend, you want to keep the bends at 45 degree because it reduces the impedance mismatch. If you get close to one of these bends, if you could measure very accurately the distance from here to here, this distance here, which is the width of the line, if you could measure this, the thing is delaying my okay, let's go back to it. Yeah, this width of the trace is lower than this width here across the elbow of the bend. And because the width here is larger, the impedance is lower. So you have an impedance change going through the bend. It would be much worse if you had a 90-degree bend. So to minimize the impedance mismatch, you do it at 45 degrees, and you try to keep the number of bends as low as possible. For instance, in this part here, this has no bends. But if I would move this a little bit more to the right, I would have to create an extra bend. So you try to minimize the number of direction changes, and the direction changes you do need, you keep them at 45 degrees, and you keep the lines as short as possible, and then you try to make the board as thin as possible so that the top layer is as close as possible to inner one. So the electromagnetic field fringes, they couple vertically and not sideways, which would lead to crosstalk. And also to keep the bottom layer vertically as close as possible to inner 2, so that the EM field fringes of these traces here, they coupled to the field to the plane above as opposed to sideways to each other. So the larger the distance between the traces and the reference plane underneath or above, the worse will be the coupling between the signals on the traces and the reference plane, and the easier the signals will couple to each other, which is undesirable and leads to interference and bad-looking signals. And the final thing is you want the TVS diodes to be very close to the points that are exposed. So if this TVS diode here is protecting this pin, you want it to be physically close to the pin it's protecting and not on the other side of the board, because otherwise an electrostatic discharge on this pin will cause damage before it gets to the diode. So little things like this. So this is pretty much it. I hope this has been useful and it helps you with your own designs of PCBs, and now you know a little bit more about how Agon was built. So take care, and I will see you next time.